Hello, and welcome to this session where we are eventually building up to our frequency domain dynamics, a complete development of all the logic involved there. So we are taking this step by step, starting from the very, very basics and looking here at Euler's formula. We know that if we have some complex number, let's call it alpha, and that, of course, has the real part, which we'll call A, and the imaginary part, which we'll call B. And then according to Euler's formula, if we take the exponential of that complex number, and in this case, we are taking the complex number times t, and t is a real number, then alpha times t can be rewritten as a to the t, a times t plus b times t. So now our real part is AT and our complex part is BT. Then according to Euler's formula, we take the real part as an exponential out here. And so this needs to be an e to the AT. And then the complex part shows up with the cos and sine functions here. So there will be a cos of BT, again, B is the imaginary part. So there'll be a cos of BT, and that will be a real part, and then plus an imaginary part, and that will be sine of BT. So that's Euler's formula, and it may seem kind of mysterious to us, or it may seem almost like a definition or something like that. Well, it's not a definition. We are actually going to test it out now, because we always have at our disposal for any function the Taylor series. So we can gain insight into any function by expanding it into the Taylor series and looking at its values in different ranges and so on. So the Taylor series or Maclaurin series for the exponential function can be expressed this way. So you can go back to your Maths 1 notes and have a look at that expansion, but let's take it as a given that the exponential of alpha t, and in fact, this should be without the t here. So the exponential of alpha is alpha to the 0 divided by 0 factorial plus alpha to the 1 divided by 1 factorial, alpha squared over 2 factorial, and so on. So the point of this is we are not applying any of the transcendental functions here. These are all nice algebraic functions, right? So if alpha is some number, let's say 3, for example, then this is simply 3 squared. There's 3 there, and 2 factorial is, of course, 4. 1 factorial is 1. 0 factorial is 1. So these are all numbers. There's nothing but multiplication and division and so on going on here. And of course, this is an infinite series. That's where it becomes transcendental. But anyway, this is, we are going to truncate this function. We are not, of course, numerically able to go off to infinity. So we will cut this short at some stage. And so we will take a finite series as an approximation to the exponential function. So to do that, I've written some short Python code here. And so here's, well, we're just using NumPy and matplotlib. So nothing out of the ordinary there either. And let's create a Taylor series expansion function here. So this is for the exponential function specifically. So as we've just said, it's the value raised to the power I. So you can see here, this time we let the value be x. So x raised to the power I divided by the factorial of I, right? So divided by I factorial. And in Python, you can use numpy.math factorial to do that. So this is the same as the Maclaurin series. And you can see here, we initialize the sum and we add it up and we go until n terms. So that's a function that's ready for us here. And let's vary x. Let's let x vary in this range. So we start at -2 and we go up to 2. We'll use 1,000 points. And so we can use the Taylor series expansion to calculate the exponential of that x. And we do that here. We can also try using the exponential function itself. So in the NumPy library, there is an exponential function. And so we can just test this out. We can try our kind of homemade Taylor's expansion here. We can benchmark that against the built-in Python exponential function. And so we calculate the same thing two ways, and we call it y and ym, and then we plot them here. So if you run this, and in fact, the lines are lying one on top the other. So let's provide it with a small offset here. Let's add a 0.1 just to make it different enough that we can see there are two curves here so that we can see that. Right, so it seems our Taylor series function is working correctly, right? So this is just a test to see if we've written this function correctly. Now let's apply it with our imaginary numbers. So let's say we have the same case as we've shown here. So we've got e to the alpha t, e to the alpha times t. And so let's fix a constant that we multiply with time. So here, let's pick this constant. So we read this as -2 plus 2i, right? So that's the convention in Python. You can include your imaginary parts like this. So 1j, and then your coefficient for that, you multiply there. So this is a constant alpha, and then we are defining t over the range 0 to 10 using 500 points, right? So that's a linspace. And we can go ahead and use our homemade function here. So we will evaluate the exponential values using the exponential pt. And we are using 80 terms here. Remember, the second term, this n here, is the number of terms, the number of Taylor series terms. And in fact, yeah, I forgot to do a check like that. Let's say we use only one term. Then you can see we don't get a very good approximation. Let's try 2 terms. It's starting to look a little better. 3, 4, 4. And so we're getting closer and closer to the function. So if we use something like 20 terms, then the lines lie right atop each other. So here we are using as many as 80 terms. And so that's our approximation of e to the pt. And then we are also evaluating it using the inbuilt Python function, the NumPy function exp. So that those are 2 ways to calculate it. And then the third way is, of course, using Euler's formula. So this is the reason we are doing this. We want to actually check whether it agrees with this function. So we have 2 ways of just evaluating it by brute force using Euler. And here you have to do a little bit of extra work just to extract the real parts and imaginary parts. So here you can see I'm extracting the real part of y. So using np.real. So in NumPy, there's a real and imag. So real and imaginary, those help you extract those 2 parts there. And let's not worry about the offset for now. And then we just go ahead and plot our results here. So YR, that's the real part. And then we've also got YE. So YE we've calculated from the built-in Python library. And here we are plotting the real parts. So in this first plot, we are just plotting the real parts. And so here's now using Euler's formula. And let's just check that this is correct. So we want a term out here, which is e to the power pt, right? And it's e to the power real part of p times t. So that's this part here, right? E to the at. A is the real part of our constant. And so that's what we have here. And then the real part of this is cos bt. So here's cos of the imaginary part, right? So all of this is the real part. And so we are calculating the real part 3 different ways here. And in the second plot, yi has been extracted. So the imaginary parts from our Taylor series approximation. Then we've also calculated y using the built-in Python function ye. So we need to extract the imaginary parts here. And then here's using Euler's formula. So there's the imaginary part here. We still do need to multiply by e to the at. So you can see that here. Here's e to the at, right? The real part is the a, so at, e to the at. And then inside here, we've got sine of the imaginary part, which is b, sine of the b times t, right? So that's the imaginary part here. And like before, we added a small offset because the lines were lying one on top of the other. So here I'm doing it again. So there's offset of 0.01. So I'm adding the offset to the second part here and subtracting it off in the Euler part there. And let's run this. And we can see here the lines follow the same shape. And if we drop the offset to a 0, then the lines are lying one on top of the other. There is a tiny little offset, and that's probably because it is an approximation, a Taylor series approximation. Okay, so it seems that it agrees, right? So even though we have used algebraic functions as our approximation to the exponential function, we are finding that e to the alpha t, where alpha is generally complex, that is giving us the expected outcome there. And so I'll link, as they say, a link in the description that will include the Dropbox link to this to this function. And so you can play around with maybe trying different ranges of things and trying different complex numbers to see if this still holds up. Okay, so with that, I hope we have satisfied ourselves that this is correct. It's not from definition or something like that. That e raised to the power complex number will give us a real part times these trigonometric functions, right? So that we haven't proven, and there are proofs available, but we've at least demonstrated numerically that it's consistent for now. Okay, so we are going to take Euler's formula as a thing that's at least been demonstrated. And of course, we are going to apply it to, first off, the simple scalar linear ODE. So if it's a linear ODE and it's scalar, that means you have just one equation. And so it's going to have the form dy dt. It's linear, so it's some constant times y. And we know that generally has the solution. And so the time constant in the original problem, this alpha, will appear as the constant with the t in the exponential here. So that's our solution. And as we've just said here, according to the Euler's formula, this can be expanded like so, right? If there is no imaginary part to this, then of course the b will be 0, and so sine of 0 is 0, so there won't be an imaginary part. And then cos of 0 is a 1, leaving us with just this part, which perhaps we're more familiar with in the scalar case where we don't have complex numbers for the constant. But generally speaking, if alpha is a constant, and we'll see later on, alpha does sneak in many different places. Complex numbers for alpha sneaks in different places, then we'll need this more general formula. Okay, so I hope that at least gives us some motivation to keep using Euler's formula, and we can see it might arise later on. Thanks for listening.